Electron-rich alkenes react with electron-poor borane reagents to produce alkyl boranes in a regioselective fashion and through a syn-addition process. The alkyl boranes are then oxidized using a basic peroxide mixture to give alcohol products that are the overall equivalent of Anti-Markovnikov addition of water to the original alkene. The regiochemical and stereochemical outcomes of these steps provide evidence for the mechanistic pathways involved. Reagents such as parachute borane, otherwise known as 9-BBN, add to alkenes to give the products of syn-addition. This stereochemical outcome is evidence for a concerted addition. Regioselectivity is also observed, in which the boron adds to the less crowded end of the alkene. This is explained by the larger groups avoiding each other in the lowest energy transition state. Oxidation of the alkyl borane with basic peroxide then provides the alcohol through a concerted migration step. This pathway is deduced from the observed stereochemical retention. Since the borane reagent features a 6-electron boron, it will undergo a Lewis acid-base interaction with an alkene. This then allows for synchronous addition and the formation of 2 new sigma bonds. If the starting alkene is prochiral, only 2 products are formed, which are related as enantiomers. This is firm evidence for the concerted nature of the addition. The larger end of the borane adds to the less crowded end of the double bond, so the observed regioselectivity is mostly governed by steric factors. A basic mixture of hydrogen peroxide and sodium hydroxide is then applied to the alkyl borane product mixture with a fast acid-base reaction producing the nucleophilic peroxide anion in a preliminary step. The nucleophilic peroxide anion then attacks the electron-poor boron on the borane to produce a 4-valent borate adduct that is now negatively charged. Since the borate adduct features a weak oxygen-oxygen bond, it will be prone to collapse, with the weak bond being cleaved. The only realistic pathway for this to occur in a basic reaction medium is for the hydroxyl group to break away with concomitant alkyl migration to the remaining oxygen. The retention and stereochemistry observed is evidence for this step being concerted. Once the 6-electron boron has been reformed, it is able to be attacked by hydroxide in the solution to give a new species that is again negatively charged. This is then ready to release the alkoxide in the final steps of alcohol formation. Loss of the alkoxide anion into the basic reaction mixture releases the borinic acid byproduct. The stereochemistry of the carbon to oxygen bond in the alkoxide has been retained from the earlier migration step. The racemic mixture obtained in this example is a consequence of the original borane addition to the prochiral alkene precursor. Finally, proton transfer from the water solvent affords the racemic mixture of alcohol products. The stereochemistry was installed in the initial syn-addition of the borane, and the regioselectivity was a consequence of larger groups avoiding each other in the lower energy transition state for that addition. In summary, addition of alkyl boranes to alkenes is a convenient method for adding the elements of water with anti-Markovnikov regioselectivity. Prochiral alkenes afford racemic mixtures of syn-addition products, the stereochemical integrity of which remains intact throughout the subsequent migration and hydrolysis steps on the way to the isolated alcohol products. The stereochemical outcomes observed in the 2 steps of this process provide important evidence for the mechanistic pathway involved.